Hello, everyone. Today, I will introduce the content related to Peripheral. This training report covers two main topics. First, a general introduction will be provided. Next, a brief overview of each peripheral module will be presented. It should be noted that this report primarily contains introductory content. For more detailed technical information, you can refer to the SDK online documentation. This section contains links to the SDK online documentation. The documentation includes API reference and peripheral sample. The API reference documentation primarily introduces the usage of APIs, while the sample documentation mainly presents commonly used samples. First, a general introduction. The initialization of peripherals mainly involves the following steps. Step 1. Set the peripheral's PINMUX and pad configurations. Step 2. Enable the clock signal for the peripheral. Step 3. Configure the initialization parameters of the peripheral. Step 4. Determine whether to enable interrupt and NVIC. Step 5. Enable the peripheral. This flow ensures proper setup and activation of the peripheral device. The APIs for pad and PINMUX are as follows. You can use pad config and PINMUX config API to set the state of the pins as needed. More detailed information will be introduced in the pad and PINMUX section. This part describes the setting of peripheral clock. It is necessary to enable the corresponding clock when activating the peripheral. Otherwise, the registers of the module will not be set properly. If you don't need to use the peripheral, you can also turn off the clock. This section introduces the general initialization process of peripherals. To facilitate parameter configuration, each peripheral provides an initialization structure in which parameters can be configured based on specific requirements. The following example is based on the GPIO. You can configure input or output functions, interrupt trigger conditions, and interrupt polarity. This section introduces the configuration of interrupts and the NVIC. You can call the interrupt config function to enable or disable interrupts as needed. The following example is based on the GPIO. If you want to enable or disable the input interrupt, you can refer to the following code. If you want to configure NVIC interrupt, you need to initialize the NVIC module. The following common peripheral modules are introduced in turn. This page shows the abbreviation of each module and its full name. First, we will introduce pad and PINMUX. PINMUX allows SoC with limited pins to use them for various functions such as SPI, I2C, and the other peripherals. Pad is used to control pin behavior. The features of pad and PINMUX are as follows. Point 1. The operation modes can be PINMUX mode and software mode. Point 2. The power configuration can be power on or power off mode. Point 3. The resistor's pull state can be pull up, pull down, or no pull. Point 4. In software mode, the output can be either high level or low level. Point 5. Each pin can wake the system from DLPS mode on high or low level. The pad can be configured as PINMUX mode and software mode. Only when the pad is set to PINMUX mode can this pin be connected to the core domain to achieve pin multiplexing. As shown in the figure. The PINMUX circuit and peripheral modules are in the core domain and will be powered down during low power mode, so they cannot work in this state. The pad circuit is in the AON domain and will not be powered down during low power mode, so the pad can work normally as in this state. The pad is mainly used to maintain the pin output state or wake up the system in low power mode. This section primarily introduces the parameters of the API related to pad configuration. Through this API, you can configure various aspects of the pad, including its operational mode, power mode, input or output status, and pull status. This section primarily introduces the configuration interface for PINMUX. The interface has two key parameters, pin and pin function. Next, we will introduce GPIO. GPIO stands for General Purpose Input-Output. Features of GPIO include: Point 1. It consists of a group of 32 pins. Point 2. It can be configured as input or output mode. Point 3. In output mode, they can be further configured as push-pull or open-drain output. Point 4. It supports interrupt functionality, with selectable trigger conditions including level-triggered or edge-triggered interrupts, as well as configurable interrupt trigger polarity. Point 5. It supports debounce configuration to enhance signal stability. The configuration process for GPIO output mode is as follows. Step 1. Configure the pad and PINMUX. Step 2. Enable the GPIO clock. Step 3. Fill the required GPIO output parameters into the GPIO initialization structure. Step 4. Use GPIO control functions. For example, you can call the GPIO write bit function to control the output level of the GPIO. Or you can call the GPIO read output data function to read the current output status of the pin. The configuration process for GPIO input mode is as follows. Step 1. Configure pad and PINMUX. Step 2. Enable the GPIO clock. Step 3. Fill the required input parameters into the GPIO initialization structure and configure GPIO as input mode. Step 4. Call the GPIO read data function to read the current pin level. The configuration process for GPIO interrupt mode is as follows. Step 1. Fill the required input parameters into the GPIO initialization structure. Configure the pin as GPIO input interrupt mode. Set the corresponding interrupt trigger conditions. Step 2. Enable NVIC. Step 3. Enable GPIO interrupt. Step 4. When the pin's level meets the set interrupt conditions, it will trigger an interrupt and enter the interrupt handler. In the interrupt handler, disable the interrupt and clear the interrupt flag. Add user code as needed. Choose whether to enable the interrupt again. If you want the interrupt to occur repeatedly, you can re-enable the interrupt. This section introduces the debounce functionality of GPIO. The debounce time is related to the count limit parameter in the structure. This relationship can be expressed by the following formula: debounce time equals count limit plus 1 multiplied by debounce clock period. An interrupt is triggered only when the pad input pulse width meets or exceeds count limit plus 1 multiplied by 2 ticks. No interrupt will occur if the pad input pulse width is less than count limit multiplied by 2 ticks. Next, we will introduce timer and PWM. The timer has the following key features. Point 1. Each timer has independent clock division capabilities. Point 2. Users can select from various clock sources. Point 3. It supports 2 counting modes, free run and user-defined. Point 4. Each timer supports PWM output mode. Point 5. It uses a 32-bit down counter. Point 6. It supports timeout interrupt. Point 7. It can generate complementary PWM outputs and support dead zone control. The timer comprises a 32-bit automatic load counter. Each timer operates independently without sharing any resources. They can operate synchronously together. The timer can operate in two modes, user-defined mode and free-run mode. In user-defined mode, the timer counts down from the value set by the user. In free-run mode, the timer counts down from the maximum value. When the timer counter is enabled, the timer counts down from its initial value. And when it reaches 0, an interrupt is triggered. Each timer supports PWM output. Timer 2 and 3 also support complementary output and dead zone. The basic operation process of timer is as follows. Step 1. Enable the timer clock. Step 2. Initialize the timer structure, including setting the timing duration and mode. Step 3. Enable the timer interrupt. Step 4. Enable the timer. Step 5. Wait for interrupt trigger. When the counter value decreases from the set value to 0, it will trigger the timer interrupt. In interrupt handling. First, clear the interrupt flag. Second, add user-defined code. The operation process of PWM is as follows. Step 1. Initialize pad and PINMUX. Step 2. Initialize timer structure, enable PWM function and set count values for high and low levels. Step 3. Enable the timer. Then the pin will output corresponding PWM waveform. If you want to modify PWM duty cycle, you can call PWM change API. Next, we will introduce enhanced timer. The enhanced timer has the following features. Point 1. Each enhanced timer is a 32-bit counter. Point 2. Each enhanced timer supports one-shot mode. Point 3. It has 3 modes, free-run mode, user-defined PWM auto mode, and user-defined PWM manual mode. The counting method varies according to the selected mode. In free-run mode, the count value is incrementing, while in user-defined mode, the counter value is decrementing. Point 4. Each enhanced timer supports PWM functionality. Point 5. The PWM output polarity can be set to start as either high or low level. Point 6. It supports outputting all high or all low levels. Point 7. Each enhanced timer supports complementary outputs. Point 8. It supports capturing GPIO levels and outputting specific waveforms. Enhanced timer is a 32-bit counter capable of dynamically generating PWM waveforms. Each channel is independent and can operate simultaneously. The main functions of the enhanced timer include 3 types. The first major function is the counting function, which is divided into 2 modes, free-run mode, where the count is incrementing, and user-defined manual mode, where the counter is decrementing and users can set the timing period. The second major function is the PWM function, which can be configured in auto mode or manual mode. These 2 modes have differences in the registers that are written to. The third function is the latch count function, which can capture external GPIO signals. In this configuration, the enhanced timer is set to free-run mode. The configuration process of enhanced timer is as follows. Step 1. Enable the timer clock signal. Step 2. Initialize the timer structure, including setting the timing count value in the max count parameter. Step 3. Enable the timer interrupt. Step 4. Enable the timer. Step 5. Wait for interrupt trigger. When the counter value counts down to 0, it will trigger the interrupt. In interrupt handling, first, clear the interrupt flag. Second, add user-defined code. Manual mode initialization process. Step 1. Enable PWM function in the initialization structure. Step 2. Set the count value for one period, which is max counter. Step 3. set the count value for high level, which is CC value. Step 4. Enable the timer. Step 5. Output the corresponding PWM waveform. Auto mode initialization process. Step 1. Set the count value for 1 period in the initialization structure. Step 2. Use the enhanced timer write CC FIFO function to set specific PWM waveform output. You can enable PWM complementary function to output PWM-P and PWM-N waveforms. In auto mode, PWM can be paired with DMA to output fixed waveforms. To do this, you need to enable DMA in the initialization structure parameters and activate the DMA module. Once DMA is started, it will transfer data from the source to the CCR FIFO of enhanced timer. It allows for the output of fixed PWM waveforms. GPIO latch count feature configuration process. Step 1. Configure enhanced timer initialization structure parameters. Set the enhanced timer to free run mode. Specify the input GPIO pin. Set the threshold for received data. Configure the trigger conditions. Step 2. Initialize enhanced timer with the configured parameters. Step 3. Configure the interrupt. Clear the GPIO latch count interrupt flag. Enable the GPIO latch count interrupt. Step 4. Start the enhanced timer. Step 5. Wait for interrupt trigger. Interrupt is triggered when received data reaches the set threshold. Step 6. Read captured data in the interrupt handler function. Next, we will introduce UART. UART provides a flexible method for full duplex data exchange with external devices. The basic features of UART include the following. Point 1. It supports 1-bit or 2-bit stop bit. Point 2. It supports data formats of 7-bit and 8-bit. Point 3. It allows for configurable parity check. Point 4. It supports hardware flow control with CTS and RTS. Point 5. The baud rate is programmable. Point 6. It supports both transmit and receive DMA. The data format of UART is shown in the diagram. Each data frame starts with a start bit, followed by data transmission, a parity bit, and stop bits. Support hardware flow control. RTS flow control. The UART receiver signals its readiness to receive data by setting the RTS pin to a low state, indicating a valid condition. When the receive FIFO data reaches the trigger level, the RTS pin output high state, signaling an invalid condition and indicating a stop to data transmission. CTS flow control. Prior to transmitting each frame, the transmitter monitors the CTS signal. When CTS is low, indicating a valid state, data transmission proceeds. Conversely, if CTS is high, signaling an invalid state, the transmitter suspends further data transmission after completing the current frame. This table serves as a reference guide for configuring settings of commonly used UART baud rates. It's important to note that the transmit error tolerance for UART baud rates is plus or minus 0.4%, while the receive error tolerance is plus or minus 3%. The UART interrupt system includes several types of interrupts, each with a unique interrupt ID and specific trigger conditions. For receiving operations, two main interrupts are primarily used. First, data receive available interrupt. This interrupt has two trigger conditions. One is that the received data in the receive FIFO reaches the preset threshold. The other is that there is at least 1 byte of data in the receive FIFO, and no additional character has been received for a duration equivalent to the transmission time of 4 characters. Second, data receive idle interrupt. This interrupt is triggered when the receive FIFO remains empty, and no new data has been received for a duration exceeding the specified timeout period. Additionally, the data receive line status interrupt is used to indicate error conditions during reception. It can be triggered by 3 types of errors: parity error, framing error, break error. The UART initialization process is shown in the diagram. Here are the steps. Step 1. Enable the clock signal for the UART. Step 2. Set the UART baud rate. Step 3. Configure the UART's parity bit, stop bit, and data bits. Step 4. Optionally, set up hardware flow control. Step 5. Set the UART interrupt trigger level. Step 6. Initialize the UART peripheral based on the parameters set in the previous steps. Step 7. Configure the UART interrupts. Here is an introduction to the UART data transmission and reception processes. UART data transmission process. After polling the transmit FIFO empty flag to check if the transmit FIFO is empty, call the UART send byte function to transmit data. UART data reception process. Check if the receive data available flag is set, then call the UART receive byte function to receive data. UART can also be configured to enable interrupts for data reception. For receiving variable length data, you can enable the data receiving available interrupt and the data receiving idle interrupt. Once these interrupts are enabled, a UART interrupt will be triggered whenever data is received. The handling process after entering the interrupt is as follows. When data is received, it triggers the data receiving available interrupt. The interrupt number is read, and if the data exceeds the set FIFO threshold, the process enters the level reach interrupt. If it does not exceed the threshold, it enters the timeout interrupt to handle the remaining data. When the FIFO is empty and the preset timeout period is exceeded, the idle interrupt is triggered. If you want to use DMA with UART for data transmission, you need to enable DMA in the UART initialization structure, and then initialize the DMA configuration according to your requirements. Next, we will introduce DMA. DMA is used to provide high-speed data transfer between peripherals and memory or between memory and memory. The data transfer can be done independently of the CPU to reduce the CPU overhead. Here are some features of DMA. Point 1. For transfer directions. Memory to memory. Memory to peripheral. Peripheral to memory. Peripheral to peripheral. Point 2. Maximum transfer size. The maximum size for a single transfer is 65,535. If the data length exceeds 65,535, multi-block transfer can be used. Point 3. Controllable channel priority. DMA supports prioritization of channels based on control settings. Point 4. Support for transfer pause and interrupt. It allows the pausing of transfers and supports interrupt handling. Point 5. Block transfer configuration. DMA can be configured for single block transfers or multiple block transfers. When DMA transfers data between peripheral and memory, a handshake configuration is required. Each supported peripheral has its own handshake number in DMA. The DMA initialization configuration process is as follows. Step 1. Configure the DMA transfer direction, data format, and the number of data items to transfer. Step 2. Set the memory address. Step 3. If transferring data between a peripheral and memory is needed, set the transfer direction and the handshake information for the peripheral. The flow for DMA single block transfer is as follows. Step 1. Enable the DMA clock signal. Step 2. Initialize the DMA structure. Step 3. Enable the DMA transfer completion interrupt. Step 4. Start the DMA. Step 5. When the transferred data length reaches the set buffer size, an interrupt is triggered. Step 6. Perform data processing and other operations in the interrupt function. Next, we will introduce RTC. The RTC has the following features. Point 1. A 12-bit prescaler. Point 2. A 32-bit counter that is incrementing. Point 3. It supports 4 comparators. Point 4. It can wake up the chip from DLPS mode. Point 5. For configurable interrupts. Comparator interrupt. Tick interrupt. Overflow interrupt. Prescaler interrupt. The configuration process for the RTC tick interrupt is as follows. Step 1. Set the prescaler value for the RTC. Step 2. Enable the RTC prescaler interrupt. Step 3. Enable the NVIC interrupt. Step 4. When the RTC counter value increments from 0 to the set prescaler value, a tick interrupt will be triggered, then it will enter the RTC interrupt handling process. The configuration process for the RTC comparator function is as follows. Step 1. Set the prescaler value for the RTC. Step 2. Set the comparator value. Step 3. When the comparator value reaches the user-defined value, a comparator interrupt will be triggered. Then it will enter the RTC interrupt handling process. The overflow process for the RTC is as follows. Step 1. Enable the RTC overflow interrupt. Step 2. Enable RTC function. Step 3. When the RTC counter value exceeds the 32-bit counter limit, the overflow interrupt will be triggered. Then it will enter the RTC interrupt handling process. Next, we will introduce LPC. LPC can be used for voltage detection. When the voltage of the pin meets the interrupt trigger conditions, the system will enter the LPC handler. The LPC has the following features. Point 1. It has 8 external channels and 1 internal channel. Point 2. It can perform high and low level detection. Point 3. It can wake up the system from DLPS. Point 4. It supports configurable debounce settings. The operation process of the LPC comparator function is as follows. Step 1. Configure PINMUX and pad. Step 2. Initialize LPC based on the set parameters. Set the LPC input channel. Set the trigger edge condition. Set the voltage threshold. Step 3. Enable the LPC comparator interrupt. Step 4. Enable LPC. Step 5. Enable NVIC. Step 6. When the voltage meets the trigger condition, it will enter the LPC interrupt handling process. Next, we will introduce AON QDecoder. As shown in the figure, the AON QDecoder is used to detect the motion state of rotary sensing devices. When the rotary device moves, it outputs 2 quadrature signals, PHA and PHB. The AON QDecoder determines the rotation direction by detecting the phase changes of PHA and PHB. The AON QDecoder has the following features. Point 1. 2 input phases. Point 2. 1 independent axis. Point 3. Hardware debounce setting. Point 4. 16-bit accumulation counter. Point 5. It can wake up the system from DLPS. A rotary device can have phase changes in 2 directions. In the forward direction, the phase changes from 00 to 01 to 11 and then to 10. In this direction, the counter's value will increase by 1. In the reverse direction, the phase changes from 00 to 10 to 11 and then to 01. In this direction, the counter's value will decrease by 1. The operation process of the AON QDecoder is as follows. Step 1. Initialize the AON QDecoder. Set whether to enable debounce and the debounce time. Set whether to count after 1 or 2 phase changes. Step 2. Enable AON QDecoder interrupts. Step 3. Turn on the AON QDecoder. Step 4. Enable NVIC. Step 5. Wait for interrupt trigger. Note, when a phase change is detected that doesn't follow the correct sequence, for example, changing directly from 00 to 11, it will trigger an illegal interrupt. Upon entering the AON QDecoder interrupt handler, you can determine whether it is due to a new data interrupt. You can retrieve the direction of the phase change and the count value. If illegal data is detected, the system will enter the illegal interrupt as well. Next, we will introduce ADC. ADC is used to convert analog signals into digital signals. ADC has the following key features. Point 1. It supports 1 internal channel, UART. Point 2. It supports 8 external channel. Point 3. It supports 2 operation modes, one-shot mode and continuous mode. Point 4. The voltage range is 0 to 900 mV for bypass mode and 0 to VBAT mV for divide mode. Point 5. It supports 16 schedule tables. Point 6. It supports hardware averaging function. The configuration process for single sampling with an ADC is as follows. Step 1. Configure the ADC sampling time, the channel to be sampled, and the schedule index. Step 2. Choose whether to enable bypass mode. Step 3. Enable the interrupt for sampling completion. Step 4. Enable NVIC. Step 5. Turn on the ADC. Step 6. When sampling finishes, it generates an interrupt. The sampled data is received in the interrupt handler. The ADC can also use DMA to transfer sampled data in continuous mode. To do this, initialize the ADC structure parameters. If you want to use continuous sampling mode, you need to specify storing the sampled data in the FIFO, and then initialize the DMA. The DMA will then transfer the sampled data from the ADC's FIFO to the specified address. Once the sampled data is acquired, you can call the function ADC getVoltage to convert the sample values into actual voltage values. Next, we will introduce KEYSCAN. KEYSCAN needs to be used with an external key matrix. The function of KEYSCAN is to efficiently and accurately detect key presses and releases across a matrix of keys. The KEYSCAN module has the following features. Point 1. It supports a configurable matrix with a maximum size of 12 rows by 20 columns. Point 2. It supports a configurable scan clock. Point 3. It supports a configurable debounce time. Point 4. It supports a configurable scan interval. Point 5. It supports a configurable all-key release detect time. Point 6. It supports automatic mode scanning and manual mode scanning. In manual scanning mode, key scanning is triggered only once. After the first scan is completed, a scan completion interrupt is triggered. If the interrupt is not cleared, the next key scan cannot be triggered. In automatic scanning mode, after a key is pressed, scanning continues at set intervals until all keys are detected as released. An all-release interrupt is triggered. The scanning interval time, debounce time, and release time can all be configured during initialization. The initialization and configuration process for the KEYSCAN is as follows. Step 1. Enable the clock signal for the KEYSCAN. Step 2. Configure the pad and PINMUX. Step 3. Initialize the KEYSCAN structure. Step 4. Specify the number of rows and columns to be scanned. Step 5. Select the scan mode and decide whether to enable debounce. Step 6. Enable the interrupt for scan completion. Step 7. When a key press is detected, an interrupt is triggered, and the system enters the interrupt handler. In the interrupt handler, the data for the pressed key can be received. Next, we will introduce SPI. SPI includes SPI master and SPI slave. SPI master has the following features when acting as a master device. Point 1. It supports 4 transmission modes: full duplex, transmit only, receive only, EEPROM. Point 2. It supports 4 clock modes. Point 3. The maximum clock frequency of SPI 0 is 50 MHz, and the maximum clock frequency of SPI 1 is 20 MHz. Point 4. The SPI frequency is obtained by dividing the SPI clock source, with divider values ranging from 2 to 65,534. Point 5. The length of transmitted data can be from 4 bits to 32 bits. Point 6. It supports hardware chip select function. Point 7. It supports DMA. When operating as a slave device, the SPI has the following features. Point 1. It supports 4 different transfer modes. Point 2. The maximum clock frequency of SPI slave is 20 MHz. Point 3. The data transfer length can range from 4 bits to 16 bits. Point 4. It supports DMA. SPI supports the following 4 transfer modes. In full duplex mode, SPI allows simultaneous transmission and reception of data. In transmit-only mode, SPI supports only data transmission. Received data is not stored in the FIFO. In receive-only mode, SPI supports only data reception. In EEPROM mode, similar to full duplex, both input and output modes are supported. However, the difference is that the data transmission sequence is fixed. Data is sent first and then received. Moreover, data is not received into the FIFO while sending data. The SPI initialization steps are as follows. Step 1. Set the PINMUX and pad. Step 2. Enable the SPI clock. Step 3. Initialize the SPI based on the configured parameters. Set the SPI transfer mode. Set the SPI data frame size. Set the SPI clock polarity. Set the SPI clock phase. Set the SPI speed. Choose which serial protocol to use for data transmission. Step 4. Enable the SPI. After the above SPI initialization steps are completed, if you want to send data, you can directly call the Send Data API. If you want to receive data, you can enable the data reception interrupt, which will be triggered when the received data reaches a set threshold. In the interrupt handler, you can obtain the length of the received data and process the data. Next, we will introduce I2C. I2C is a 2-wire serial interface, consisting of a serial data line and a serial clock. These wires carry information between the devices connected to the bus. The I2C has the following features. Point 1. It supports I2C master mode and slave mode. Point 2. It supports 7 bits or 10 bits address mode. Point 3. It supports standard mode, fast mode, and fast mode plus. Point 4. It supports DMA transmit and receive. In an I2C master device, there are 3 transmission modes. The first mode is master write. The master initiates a start condition and then sends the slave address accompanied by a write bit. The slave responds with an ACK signal after receiving the memory address. Once the master receives the ACK, it continues transmitting data. After the master sends the last byte, it sends a NAC signal to indicate that all the data to be written has been sent. The second mode is master read. The master initiates a start condition and then sends the slave address with the read bit attached. The slave device responds with an ACK signal after receiving the memory address. Then, the slave sends data to the master, and the master sends an ACK signal in response. When the master receives the last byte, it sends an ACK signal, indicating that data reception is complete and no more data needs to be sent. The second mode is master repeat read. In this mode, the master device first sends data and then receives data. After the master completes sending data, it continues by sending a restart signal. Then, it starts receiving data. I2C master initialization process is as follows. Step 1. Set clock speed. Step 2. Set transmission mode to master mode. Step 3. Set address format. Step 4. Set slave address. Step 5. Enable ACK signal. As a master, I2C provides 3 APIs for data transmission: I2C master write, I2C master read, and I2C repeat read. I2C slave initialization process is as follows. Step 1. Set transmission mode to slave mode. Step 2. Set address format. Step 3. Set slave address. Step 4. Enable ACK signal. When the slave needs to send data, it will receive a read request signal from the master, which triggers an interrupt. Within the interrupt, I2C send command is executed to send data to the master. When the slave needs to receive data, you can enable the receive full and stop detect interrupts to handle data reception within the interrupt. Next, we will introduce IR. The infrared module can realize infrared wireless communication with adjacent devices. The IR has the following features. Point 1. It supports a configurable carrier frequency. Point 2. It supports a configurable carrier duty cycle. Point 3. It supports GDMA. Point 4. Receive mode and transmit mode cannot work at the same time. Point 5. IR module must be reset when switching between receive mode and transmit mode. The IR data waveform is shown in the figure below, consisting of carrier data and empty data. The carrier frequency and duty cycle can be controlled in the initialization structure. In the IR data, bit 31 can be configured to control whether the data is carrier data or empty data, and bit 26 to bit 0 can be configured to control the duration of the waveform. Refer to T1, T2, and T3 in the figure to understand the relationship between the specific waveform and the data format in the FIFO. The IR transmit initialization process is shown in the figure, with the following steps. Step 1. Set pad and PINMUX. Step 2. Enable the clock signal for IR. Step 3. Set IR parameters, including configuring carrier duty cycle, setting carrier frequency, and setting carrier data transmission direction to transmit. Step 4. Initialize IR based on the set parameters. Step 5. Configure IR transmit FIFO level interrupt, enable IR, and initialize IR transmission data. IR transmission data can be sent using the IR send buff function. After enabling interrupts, if IR data exceeds the FIFO threshold, an interrupt will be triggered. You can process the data for transmission within the interrupt handler. If the data size is larger than the transmit FIFO threshold, the data needs to be split into multiple packets for sending. The IR receive initialization process is shown in the figure, with the following steps. Step 1. Configure the sampling frequency. Step 2. Set IR to receive mode. Step 3. Set the receive threshold. Step 4. Set the receive counter type and threshold. Step 5. Enable the receive threshold interrupt and counter interrupt. When the received data reaches the set threshold quantity, it will trigger the receive level interrupt. Data can be received within this interrupt. The IR receive buffer interface can be called to receive IR data. When the duration of a certain level in the received data exceeds the set maximum time, it will trigger the receive count interrupt. Next, we will introduce I2S. The I2S is a peripheral to support audio protocols. I2S has the following features. Point 1. It supports two numbers of interface. Point 2. It accommodates a sample rate range from 8K to 192K. Point 3. It allows for configurable data and channel lengths. Point 4. It supports the transmission of I2S, left justified, PCMA, and PCMB data formats. Point 5. The interface can be configured to operate either as a master or a slave device. Point 6. It supports DMA. The I2S interface includes the left-right clock signal, bit clock signal, and data lines for DAC and ADC. In I2S or left-justified format, this clock signal can indicate whether the data is on the left or right channel. In PCM mode, the clock can be used as a frame sync signal. This page introduces the data formats for I2S. When the transmission format is I2S format or left-aligned format, LR clock is used to distinguish between left and right channels. For I2S format data, the MSB is always transmitted on the second bit clock pulse after the LR clock changes. For left-aligned data, the MSB is always transmitted on the first bit clock pulse after the LR clock changes. For PCMA and PCMB data, LR clock is used as a frame synchronization signal. For PCMA format data, the MSB is always transmitted on the second bit clock pulse after the LR clock changes. For PCMB data, the MSB is always transmitted on the first bit clock pulse after the LR clock changes. The initialization process for I2S is shown in the figure, which includes configuring the following parameters. Step 1. Set the sampling rate. Step 2. Set the transmission mode. Step 3. Set the channel type. Step 4. Set the data width for transmission. Step 5. Set the data format. I2S data sending and receiving process is as follows. Step 1. Configure pad and PINMUX. Step 2. Initialize the I2S structure. Step 3. Enable the I2S. Step 4. When I2S receives data from an external codec, I2S with extern codec command must also be enabled to receive external data. The I2S send function and I2S receive function can be called to send and receive data. For I2S data reception, you can configure and enable the I2S receive ready interrupt. Once data is received, it will trigger the interrupt to handle the data processing. If you want to configure DMA for data transfer, you should initialize the DMA and set up the handshake information. Next, we will introduce CODEC. CODEC can convert between analog and digital signals. The decoder has two main functions. The first is uplink channel. The device has an analog microphone input and two PDM interface digital microphone inputs for recording applications. The second is downlink channel. Only in differential mode, mono DAC output can be used for connecting to an external audio amplifier. Codec I2S serves as the I2S slave interface for the internal audio codec. It supports changing the format of transmitted and received data. The uplink path is a recording processing module that includes the following parameters. Point 1. The mic type for the channel can be AMIC or DMIC. Point 2. It supports a configurable sampling rate. Point 3. It provides DC bias current for external microphone devices. Point 4. It provides dynamic control of digital gain from -17.625 dB to +84 dB. Point 5. It supports dynamic mute control. Point 6. It supports 5-band EQ functionality to adjustment and optimize the audio response. The downlink path is a playback processing module that includes the following key parameters. Point 1. Gain Control DVOL module supports attenuation from +0 dB to -65.625 dB. Point 2. Mute control can be dynamically set. Point 3. DAC dithering improves the quality of the audio signal during digital to analog conversion by reducing quantization noise and distortion. Point 4. It supports up to 10-band EQ functionality. Next, we will introduce SPI 3-wire. SPI 3-wire is used for data transmission with connected SPI 3-wire devices. It has the following characteristics. Point 1. It has half-duplex communication. Point 2. It only supports master mode. Point 3. It supports single data transmission. Point 4. It supports single or burst data reading. Point 5. It allows adjustment of delay time between read or write operations to meet the specific application requirements. Both the single write mode and single read mode consist of 2 bytes. The first byte contains the address and has a bit 7 as its MSB to indicate data direction. The second byte contains the data. In burst read mode, SPI can continuously read multiple bytes of data. Between the first byte, which is address byte, and the second byte, a delay of t-hold needs to be added. This delay is configured by SPI 3-wire read delay. There is no delay between the third byte and the second until the end of a burst read. The SPI 3-wire initialization process is as follows. Step 1. Set up pad and PINMUX. Step 2. Enable the clock signal for SPI 3-wire. Step 3. Configure the SPI 3-wire parameters. Transmission clock. Data format for transmission. Delay time for reading and writing data. Step 4. Initialize based on the configured parameters. SPI single write operation. First, check if the SPI busy flag is not set, then call the SPI 3-wire start write function. SPI single read operation. Similarly, check if the SPI busy flag is not set, then call the SPI 3-wire start read function. SPI burst read operation. To read multiple data at once, call the SPI 3-wire start read function, where the second parameter specifies the number of data items to be read. That concludes today's content. Thank you all for your attendance.